Okay, hi everyone. Today we are going over chapter 1, which is the scientific method, which is what most science courses will start with. And just so you guys know, there is the textbook reading section 1.3, which is pages 9 through 13. And these ebook readings will come before most lectures and have short pre-lecture assignments and ebook quizzes. And then these two are optional. So there are textbook review questions and engage questions on these pages. So the key concepts for this chapter are to contrast objective and subjective observations, describe the steps of the scientific method, see what 2 rules you must follow when developing a hypothesis, describe the control group in an experiment and why do we need one, interpret bar and line graphs including the use of standard error, and differentiate between inductive and deductive reasoning. So the key terminology for this chapter is hypothesis, variable, theory, and placebo. So when you are studying, these key concepts and terminology here match the study guide, so focus on these. So I'm just going to make a little note here. Take this out a little bit. Focus on these. When studying. Okay, so for the question of the day, how do you do science? So the questions of the day, for each exam, there are 3 extra credit questions, and these ask about the questions of the day for this section. So make sure you pay attention to these. And for this one, you are given a hypothesis. We'll come back to this later. And this is from your reading from the ebook. I think it's talking about stomach ulcers, but antibiotic A is more effective than antibiotic B. So again, we will come back to that in a little bit. So for the pre-lecture assignment, as you are reading your textbook on pages 9 through 12, you should be able to fill in these blanks. We'll go through this together. The first part is just talking about science. So science is a way of knowing about the natural world, and the scientific method is a systematic process to arrive at the truth. And we have the steps of the scientific method, which you guys are probably familiar with, but first we make an observation that brings up some sort of problem that needs to be solved or some sort of question to be answered. And from there, we form a hypothesis. And we use experimentation to test that hypothesis, and that hypothesis is either confirmed or it's rejected. So if it's confirmed, we can go ahead and form a conclusion. If it's rejected, we have to go back and form a new hypothesis, retest it, and keep going until we can confirm our hypothesis. So for filling in these blanks, number 1, make an observation. Objective, observations are supported by factual information and they can be observed and measured, while subjective observations involve personal judgment or preference. So step 2, developing a hypothesis. A hypothesis is a possible explanation for a natural event and is based on existing knowledge. So a hypothesis is not just some random guess. Before you form a hypothesis, you should do some sort of research about the observation that you've made or the question you have and see what's already known about it. And then you can form your hypothesis based on that existing knowledge. A hypothesis must be testable and falsifiable, meaning it can be shown to be incorrect. And these two rules are not in the textbook, so that's just something to note. And for the next step, you are ready to perform an experiment to test your hypothesis. And so that's what goes in this blank here again. An experiment is a series of procedures to test a hypothesis. A good experimental design includes an experimental variable, which is what is changed in an experiment and what is being tested. And I've always known this and taught this as the independent variable. So if you are familiar with that term, it's essentially the same thing. And then you have your treatment or test group, and this is the group that is exposed to the experimental variable. And then we need to have a control group. And this is the group not exposed to the experimental variable. So once you have done your experiment, it's time to collect and analyze the data. And the data or results are often presented as tables and graphs, which we'll look at some examples of in just a minute. And then step 5, finally, is to develop a conclusion. So make sure to complete the McGraw-Hill Connect reading quiz for this chapter. That can be accessed on Canvas. And if you haven't already, make sure you the fee for your ebook was already paid for when you signed up for the class, so you should need to go onto the McGraw-Hill on Canvas and sign up for your account there, and make sure to use your new Utah Tech email. Alright, so this says working in groups of 2. If you have someone else taking this class that you can work with, then you can work together. If not, you can do this on your own. But working in groups of 2, and this is our question of the day, use the space below to design an experiment for our hypothesis, which is that antibiotic A is more effective than antibiotic B. And make sure you identify the treatment and control groups and any variables. So what I'm going to write right now, I don't want you guys to write. This is just a separate example. Nothing to do with this hypothesis. I'm just showing you how to properly set up an experiment. So I'm going to write it on here. But again, don't copy this down. You guys will do this on your own once I am done. So we're going to set up an experiment, and let's think about flowers. So first of all, let's list the things that flowers need to grow. So first of all, they obviously need sunlight. They're going to need water. They need soil to grow in. They need carbon dioxide from the air. And we'll go ahead and leave it at that. And let's say we want to test how the amount of sunlight affects the growth or height of the plant. So our hypothesis could be something like flowers that receive more sunlight will grow to a greater height. I'm trying to think how to spell this. I before E except after C. Okay. That receive more sunlight. will grow to a greater height. So that is my hypothesis that I came up with. So how could we test this? Well, we know that we're going to need different groups. So the first group could be our control group. And this would be a group of flowers that receives no sunlight. We could just do a second group here and show flowers that receive maximum sunlight and see how they compare. I'm going to do two groups. So we will do, this may not be the greatest example, but it will still work. We'll do a group that receives minimal sunlight. And then maximum sunlight. So we'll say our minimal sunlight group will receive 2 hours of sunlight per day. And our maximum sunlight group will receive, let's say, 6 hours of sunlight per day. And so we've got our three groups. Our control, these are, this is ultimately what we're testing here. So this is our testable group. And for our controls, not to be confused with our control group, but what needs to be controlled is we want everything to remain exactly the same among these three groups, except for the amount of sunlight, which is the experimental variable that they're going to receive. So we would want to make sure they get the same amount of water, that they are planted in the same soil, they receive equal amounts of carbon dioxide, which we don't really have a control over, but if they are grown in the same area, then it should be the same. And what else? That the same seeds and plant types are used. That way, when we get our results, we can be sure that the results are from the variable that was changed and not something else that could have contributed. So it's very important to have controlled experiments. And the data we would want to collect for this is after a certain amount of time, we would want to measure the height of the flowers. And I would probably come up with an average for each group. And since this is a one-time measurement thing, and we'll get to this down here, it would probably be best to show the data on a bar graph like this. But I'm going to go ahead. I want you guys to pause it here. And in this space, I want you to do this with the hypothesis from the question of the day, which is that antibiotic A is more effective than antibiotic B. Again, make sure to identify the treatment and control groups and any variables. So make sure you tell me how many groups would you have? What does each group get? What kind of things need to be controlled? And then something else to consider. I was just talking about flowers here, but when we're talking about humans in this case, if the bacteria that is being tested or treated is life-threatening, is it unethical to give the control group a placebo, which is a pill with like no medication in it, instead of an antibiotic that is already known to be effective? So that's something to consider. And you must have a large sample size. Test this on a lot of people because everyone reacts differently. So we need to know on average how each antibiotic does. So go ahead and pause this recording and fill in this section, and then come back when you're done and we will talk about data. Okay, so data are the results of experiments, again, often represented as tables or graphs. I think tables are great for collecting and organizing data, but it's really the graphs, the picture that you can see, that makes it easy to interpret the data. So today we are looking at just two types, and there are many more types of graphs than this, obviously, but we're going to look at a line graph and a bar graph. And they usually will show standard error. That's what these marks are here. So this shows a variation between subjects represented by bars on a graph. So line graphs are best for continuous measurements over time. So you can see here on this line graph, all graphs should have a title describing what they are showing. So this one says variation in blood cholesterol levels. And on the x-axis, the horizontal axis here, we have a series of weeks. So these are measurements over time, week 1, 2, 3, and 4. And then on the y-axis, the vertical direction, we have blood cholesterol. And make sure to always include units. And this shows you how it changes over time. And each dot represents an average. Over here we have a bar graph, and bar graphs are best for one-time measurements. And on this one, the title is Effectiveness of Treatment. That's not very specific, but here on our x-axis, we can see it's labeled percentage of ulcers cured. And then percent treated over here on the y-axis. So obviously our range goes from 0 to 100%. And then we have our control group, test group 1 and test group 2. And by looking at this graph, you can see the control group, 10% of their ulcers were cured. 60% here in test group 1 and 80% in test group 2. All right, so let's look at some more graphs to make sure we can interpret the data. So working in groups of 2, again, or on your own, if you are on your own, which is fine. Let's interpret the data below. So this graph is showing average gum recession progression. So your gums in your mouth can recede over time, kind of pull away from the teeth and the roots of your teeth. And this is a line graph because we're looking at measurements over time. On the x-axis, we have years after initial onset. And over here on the y-axis, we have gum recession in millimeters. And so it asks, from this graph, can it be assumed that gum recession continuously increases over time? So if you look at year 1 here compared to year 6, did it increase? Yes, it did. So we can go ahead and say yes for this one. Periodontitis is categorized as moderate when gum recession is measured at 5 millimeters to 7 millimeters. So how many years after onset does a patient fit into this category? According to this graph, if we go up here to gum recession measurement of 5 millimeters and follow it over, you can see it hits that mark here on year 4 and continues past that to year 6. So this would be from years 4 to 6. All right, looking at this next graph, the effect of toothbrushing pressure on gum recession. So on the x-axis, we have patients who use a light brushing pressure, patients who use a moderate brushing pressure, and patients who use a heavy brushing pressure. And then again, we have the gum recession in millimeters on the y-axis. So from this graph, can it be assumed that brushing pressure has no effect on gum recession? Well, if it didn't have an effect, all of these would be the same or close to the same, but they're not the same. You can see they're very different. So can it be assumed that brushing pressure has no effect on gum recession? No. And based on the data in this chart, what advice would you give a patient who was showing early signs of gum recession? Well, what kind of pressure would they want to use when they're brushing? Probably a light brushing pressure. So use a lighter brushing pressure. Alright, so hopefully we're feeling a bit more comfortable looking at and interpreting graphs and analyzing data. And next we are going to look at different reasoning tactics that scientists use when forming hypotheses and conclusions. So we have deductive reasoning and inductive reasoning. So when you see deductive reasoning, starts with a DE, you can think of a decrease in size. So with this ones, we are going, with this type of reasoning, we are taking general observations and then taking that to make very specific conclusions. So with this, we're saying that what is true for the group is also true for the individual. So you're taking a general observation and making a specific inclusion. You're decreasing in size from a group to an individual person or sample or whatever. And with this one, your conclusion is likely correct. So deductive reasoning would be a good type of reasoning to use when forming hypotheses and conclusions. So here we have an example. This boy here is Adam, and if you know Amber Mortensen there, this is her son. And if we are to use deductive reasoning, we can say all autistic, and by the way, Adam is autistic. All autistic kids have 3 characteristics. And let's write what those are. I'll go ahead and put those up here. Difficulty socializing. Repetitive behaviors. and narrow interests. So we're making a general observation here that all autistic kids have at least these three characteristics. And using deductive reasoning, we can say by observing Adam that Adam has these characteristics. Therefore, he is autistic. So again, you're going a decrease in size, deductive reasoning, from general observations to specific conclusions, and they are likely correct. And as I'm giving you guys a minute to fill that in, let me know. This is my first time using an Elmo and recording an online lecture. So if you're having a hard time hearing me, or if you would like me to zoom in more or slow down or speed up or whatever it is, please give me your feedback so I can make this go as smoothly as possible for you guys. On to inductive reasoning. This is, think of it, starts with an IN, an increase in size. And with this, we're going the other way. We're going from specific observations to general conclusions. Sorry, Adam, I had to write on you a little bit there. So this is saying that is what is true for the individual is also true for the group. So kind of backwards from what we set up here. And with this one, conclusion may be incorrect. So we're going to look at Adam here as an example again. And Adam just loves to be touched and hugged. So if we use inductive reasoning, we could look at that specific example or specific observation from Adam and make a general conclusion about all people that have autism and say all autistic kids like to be touched and hugged. And this is not always the case. So again, your conclusion may be incorrect. If you're just taking one individual, an observation from an individual, and applying it to an entire group, may be incorrect. So again, working in groups of two or on your own, decide if the statements listed below are examples of inductive or deductive reasoning. So this first one, the steroid dexamethasone was tested in a small clinical trial and found to be effective in reducing death rates in severe COVID-19 patients. This drug will be an effective way to treat worldwide cases of severe COVID-19. So I'll give you a minute to think about that and decide if you think that statement is using deductive or inductive reasoning. All right, so this one is starting small. We're looking at a small one clinical trial that was found to be effective, and we're taking this observation to the entire group, saying that worldwide cases can be treated with this. That's increasing in size. You're going from a specific observation of one group to a general conclusion. So that's going to be inductive reasoning. And remember, your conclusion may be incorrect with this. The next one, in general, patients with pink eye, conjunctivitis, exhibit eye redness, itching, discharge, and crusting around the eyes. Sam has these symptoms, so he must have pink eye. So decide if you think that is deductive or inductive reasoning. I'll give you a couple of minutes, a couple of seconds. All right, so in this one, we're going from a general observation. In general, patients with pink eye have these symptoms, and we're making a specific conclusion about one individual. So if Sam has these symptoms, then he must have pink eye. This is deductive reasoning. And like it says above here, your conclusion is likely correct. And this last one, while making pasta, you notice that adding salt to the water makes it take longer to boil. You decide that salt, in general, must raise the boiling point of water. So decide if you think that's deductive or inductive reasoning. So this is going from a specific observation about your little boiling pot of water to a general conclusion that this is how all water behaves. So you're increasing in size. So this is going to be inductive reasoning. And again, your conclusion may be incorrect on this. All right, so moving on to our last page for the scientific method here, we've got theory. So theory is a well-defined and accepted explanation that has been confirmed through many repeated experiments. So with my 7th graders, a lot of times we'll talk about the theory of evolution, and they'll say, well, it's just a theory. And in everyday conversation, the word theory is kind of like a guess or someone's idea about something. But keep in mind, in science, it's well-defined. It's been confirmed many times by many different people through many repeated experiments, and it's never been disproven. So to get a theory, we got to go through the steps of the scientific method here. We start with an observation, form a hypothesis, conduct an experiment. If the results reject your hypothesis, you come back and form a new hypothesis. until you can confirm your hypothesis. And if this is done many, many times in repeated controlled experiments, then maybe someday we can say it's a theory. All right, so back to our question of the day. How do you do science? So example, antibiotic A is more effective than antibiotic B. So if you want to go back to that page where you wrote down how you would test this and kind of see how it compares here, what we did is first we need to state our hypothesis, which was given. Antibiotic B is a better treatment for ulcers than antibiotic A. And so we're going to divide these people into groups, and you could have done this a number of ways. But we've got 3 groups here, and you'll perform the experiment. And it needs to be a controlled experiment, so the groups would need to be treated the same way, except for the experimental variable, which is the type of medication that they received. And so you'd want to make sure they are probably of the same age range, maybe even the same gender. And there are so many things to this, it would be hard to test, but same like stress levels, same diet, they're eating the same things in order for this to be a controlled experiment. The 3 groups here shown are the control group, which would receive a placebo, which contains no antibiotic. And test group 1 could receive antibiotic A. And test group 2 receives antibiotic B. You remember our guess or our hypothesis is that B is better than A. And then to collect our data, each subject was examined for the presence of ulcers. And our results here are on this graph, which we saw earlier. So effectiveness of treatment, percent of ulcers cured, percent that were cured and treated over here. In the control group, which received a placebo with no medication, there were 10% that were treated. In the test group, which was antibiotic A, 60% were treated. And in test group 2, which received antibiotic B, so this is the one that we were testing to see if it was more effective, 80% were cured. So if you go back and look at the hypothesis, antibiotic B is a better treatment for ulcers than antibiotic A. We can say that for this particular test, the results confirm hypothesis. That B is better at A. It cured 20% more of the patients with ulcers. We would probably want to run this experiment over and over again to see if we still had similar results each time. And that is it for today. So again, if you guys had any problems like accessing this video or getting it to play or hearing me or being able to see what I write or any of that, please let me know so I can fix it for the next one. And we'll see you in chapter 2.